In this unit, we're going to take a look at what happens when ions actually bond. So we looked last time that electrons can be gained or lost to form anions or cations so that atoms can become stable. Now we're going to take that one step further. Remember, we know about elements, we know about compounds. We know elements contain only one kind of atom. We know compounds contain two or more different atoms bonded together. Well, why would they form a bond? Atoms form bonds because they want that stable configuration. They want to get to 8. Okay? So if they're stable, they're happy. It's a lower energy state. They don't have as much potential to change. That makes them good. So they form bonds to become more stable. Now remember, elements in group 1A through group 7A are incomplete. Everything in 1, 2, and 3 has a few extra valence electrons. Everything in 5, 6, and 7 needs a few more electrons, and then they can be stable. Group 4, they're kind of right in the middle. They're not going to gain or lose electrons. They don't ionize, but they can form bonds. We'll look at that later. Okay. Atoms in group 8, already stable. They already fill their outer energy level. There's no more electrons to gain or lose. They don't need any. They're not going to bond. Okay, so the noble gases are stable because their outer electrons are already filling that energy level. Now remember, like I said, compounds, different elements bonded together. Like sodium and chlorine, they bond to make sodium chloride. We're going to look about the naming rule on that in a minute. Okay. You can bond identical elements. Oxygen will form a bond with another oxygen atom, but that's not a compound. That's just oxygen because it's still just oxygen atoms. It contains only one kind of atom. Okay. So in an ionic bond, what happens? Well, remember, an ion is a charged atom, so we're going to have charged things interacting here. So charged atoms are ions, and how did they become charged? They became charged by gaining and losing electrons. So in an ionic bond, we're going to have electrons transferred from one element to another. Then that creates oppositely charged ions. And remember, opposite charges attract. So the ion has gained or lost an electron, and so metals, remember, lose electrons, and they're going to be positive ions. Nonmetals gain electrons, they're going to be negative ions, and that means a metal will stick with a nonmetal. If you see a compound like sodium chloride, NaCl, I know right away looking at that that's ionic because it's got a metal in it and it has a nonmetal in it. It has a positively charged ion and a negatively charged ion. But the compound will end up neutral because the positive anion and the negative, or the positive cation and the negative anion are going to balance. So what happens? What actually goes on here? So this says, let's show the transfer of electrons that would occur between magnesium and fluorine. Give the final formula and name. Alright, so we're going to have to learn some naming rules, we're going to have to learn some formula stuff, and we're going to have to look at how charge transfers. So the very first thing I'm going to need is a periodic table because I don't know what the charge of a magnesium atom is going to be. I don't know what fluorine is going to do. So I need to actually go to my periodic table and look this stuff up. So I have a periodic table handy, and I see magnesium in group 2A. So magnesium has 2 valence electrons. So I'm going to start with drawing my magnesium valence electron dot diagram. And fluorine is a group 7A element. It has 7 valence electrons. So it has 1, 2, 3, 4, 5, 6, 7. Okay, 2 per side, and then this side's got an open spot. Okay, so to show the transfer of electrons that would occur, well, magnesium actually has 2 electrons to give away. Fluorine only has 1 open spot. Now, I don't have to draw this, but I can see that magnesium's going to actually give one of its electrons away, and it's going to move over there. Okay, now that leaves fluorine stable, but with an extra electron, so a negative charge. That leaves magnesium not quite stable yet. It needs to give away another electron. Well, that means we're going to need another fluorine atom to take that electron. It's got its 7, and then this last one fills in here, and I have another fluorine 1 minus. Okay, so I actually end up with a magnesium 2 plus, just like I thought I would because it has 2 extra electrons, and I'm going to end up with 2 fluorine minuses. Okay, fluorine minus, fluorine minus. Now you'll notice the total charge, 2 plus 1 minus, 1 minus. That adds back up to 0. So the final charge of my compound is neutral, which is good. An ionic compound will always be neutral. The positive cation will always be balanced by the negative anions. Now, a formula for an ionic compound shows the ratio of ions in the compound. So I have Mg, one of those, and I have F, but I have two of these. You'll notice I don't have the charges listed on here. And this one is never written. Okay? If there's just one thing, you write it and you forget it. MgF2. Okay? MgF2. That's the compound. It tells me there's 1 magnesium to 2 fluorine ions in the compound. Now, I also want to name it. Okay? So this is the formula for this thing. I also want to name it. Well, naming ionic compounds is pretty easy. Okay? You write the metal first and nothing happens to it. Magnesium. Okay? You write the nonmetal second. So you always write these in the order they appear from left to right on the periodic table. Magnesium's the metal, it's on the left, it comes first. Fluorine's the nonmetal, it's right on the table, it comes second. Okay? The only thing that changes is you change the ending of fluorine, I-N-E, to fluoride, I-D-E. So you change the anions ending to ide, and that lets us know we have magnesium fluoride. Okay? That's the compound that has the formula MgF2. Now, there's another way to do this. There's an easier way, maybe, to come up with that formula. So let me show you that real quick. I'm going to go ahead and clear all this, and let's look at this again. Okay, so magnesium is Mg, and it has 2 valence electrons. Fluorine is F, and it has 1, 2, 3, 4, 5, 6, 7 valence electrons. Looking at this, you should be able to look at that and go, it's got those two, it's going to get rid of them. I end up with magnesium 2+. I should be able to look at fluorine and go, it's got an open spot, it's going to gain. So I have Mg2+, but I have F1-. How many 1 minuses does it take to balance a 2+? Well, it takes 2. So I end up writing MgF2. You'll notice it's almost like this little charge came down here and this little charge came down here. They swapped. So I've got 1, 2 fluorines for every magnesium. That works for ionic compounds. Magnesium fluoride. Okay. Let's look at another example. Okay. So electrons that would transfer between cesium and sulfur. Again, I need a periodic table for this. Cesium is a group 1 element, Cs. It has 1 valence electron. Sulfur is a group 6. It's a 6A. It has 6 valence electrons. 1, 2, 3, 4, 5, 6. Okay? Which means cesium is actually going to lose this electron and become cesium 1+. And sulfur is going to gain 1, 2 electrons and become sulfur with 8 valence electrons but a 2- charge. So just like before, I need to balance those charges. How many 1+s does it take to balance a 2-? Well, cesium, if I had 2 1+s, I could balance 1 2-. So Cs2s. Cesium sulfide, just like before, we change the name to cesium sulfide. The ending goes to IDE. This is the formula for cesium sulfide. It tells me 2 cesium ions for every sulfide ion. Okay. Give the ions that each element would form and give the formula and name of the ionic compound they would form. So, aluminum and oxygen. This one is a little bit tricky sometimes. I'm going to grab my periodic table and I'm going to look. Aluminum has 1, 2, 3 valence electrons. Oxygen has 1, 2, 3, 4, 5, 6. It's in group 6A. This one's in group 3A. I look at aluminum, it's a metal. It's less than 4. It's got 3 valence electrons. It's going to give them all away. I'm going to write aluminum 3+. Oxygen has 6. Okay? that means it'll take 2 and fill in those open spots, but when it does that, it becomes a 2 minus. Now, how many 3 pluses does it take to balance a 2 minus? Well, it takes 2 of these and 3 of those. Remember, you can just do the switch. So Al3 plus O2 minus, this is going to switch, this is going to switch, and so I end up with Al2O3. This is aluminum oxide. Aluminum oxide, because the metal always is written first, the ending of the ion or the anion changes to IDE. Okay? Potassium and nitrogen. Okay. Potassium sometimes is hard to find on the table unless you remember potassium is K. K is group 1. It's got 1 valence electron. Nitrogen is a group 5A element. It's got 1, 2, 3, 4, 5. So I should be able to look at potassium and go K is a 1 plus. Nitrogen will be a 1, 2, 3, 4. So it needed to get 3 electrons. That's a 3 minus ion. So I'm going to need 3 potassium ions for every nitrogen ion in order to get this thing back to a neutral compound. So I have potassium nitride, Nitride. Again, the ending changed to IDE. That's what happens when you name ionic compounds.